Welcome to Volume 3 of the Cenozoic, where we are going to continue looking at what fascinating geologic events were affecting parts of the world other than North America. So in Scotland and Ireland, we have massive basaltic eruptions that occur as Europe and Greenland are rifting apart. And if you ever go to the island of Staffa, this is what you'll see. These are some of the basalts that were erupted at that time. Also the Giant's Causeway in Northern Ireland. Just as a little bit of trivia for you guys, on Staffa there's a place called Fingal's Cave, which you can visit, and there was in fact a symphony written, the Hebrides, celebrating the waves and the rocks and all the beauty of these islands. So if you're ever in the mood, look that up, the Hebrides Symphony. Other things, I mentioned that we have the East African Rift. Like in part 1, I said that was kind of important. So this is where Africa is actually splitting into some pieces. And the East African Rift stretches down from, basically this is Djibouti. That's where my brother used to live and my sister-in-law's from. And we come down this way, and these are the rift valleys of that East African Rift. So over time, this area, Somalia, is basically splitting off the rest of the continent. And the Red Sea is a much better developed part of this. That's rifted off enough that we're actually getting a narrow, thin sea developing there. In the rift, because this is a volcanic area, rifts are volcanic, and you have this area known as the Danakil Depression. And you get some very fascinating things, hot springs and sulfurous areas, all related to this rift event. And it just looks sort of like a place, I don't know, it's like Dr. Seuss gone wild there, all kinds of different weird growths and stuff. Be careful, the water can be very acidic in this area. All right, Antarctica has an important role to play in the Cenozoic. If we went to Antarctica in the early Cenozoic, it would be kind of sort of tropical. It would be very much like what we have around us here in Texas. And this is partially because it was still connected to Australia in the Paleocene and Eocene. And this allowed warm water currents to travel to that area and keep things kind of warm and equable and tropical-ish. But it's split away from Australia, and in the Oligocene, those circumpolar currents developed circling around Antarctica, right, circling around our continent here and preventing warmer water currents from coming down there and bringing it any kind of warmth. So Antarctica significantly cooled. Now, in the tertiary, we have some fascinating events in the climate system. We have something known as the Paleocene-Eocene thermal maximum, also abbreviated the PETM. And what we're looking at on this graph right here, this is when the dinosaurs die out, this is today, and this line is the temperature, average global temperature. So you can see when the dinosaurs died out, we're right about here, and then we leap into this very abrupt, very sudden, very hot time of the PETM. It kind of drops, but then we have this whole extra warm time known as the early Eocene climatic optimum. And since that time, temperatures actually been dropping other than like a little rise here in the Miocene. So this PETM, why would we have had that sudden rise in average global temperature? Well, it probably has to do with methane hydrates that were on the seafloor that ended up getting released due to seafloor volcanic activity. What methane hydrates are, they are methane trapped in ice on the sea floor. These are sometimes also referred to as clathrates. These things are fascinating. If you bring them to the surface, you can hold this piece of ice and you can actually light it, because as it's melting, it's giving off methane, which is a flammable gas. And so you can light it, and you can like hold this flaming piece of ice in your hand and be like, I am the wizard of fire. And you won't burn your hand because the ice protects your hand from the flame, but it's really, really cool. And if you ever get the chance, you ought to do it. But anyway, we have this stuff that's on the sea floor, this methane, which is a strong greenhouse gas, trapped in this ice on the sea floor. But remember, I was just saying we're still having some splitting of the continents, so we've got a lot of volcanic activity on the sea floor. Well, volcanic activity is going to start melting all this stuff, right? And so we get these massive amounts of methane released into the atmosphere. Methane's that strong greenhouse gas, so we get this intense warming event at that time. All right, so what did we see? 5 to 10 degrees Celsius increase in temperature in terrestrial environments and the surface ocean, both in tropical and high latitudes. So that's a significant increase in temperature there. The sea surface temperatures near the North Pole were 23 degrees Celsius. I will swim in 23 degrees Celsius water. That's actually pretty nice. I don't know, convert it into Fahrenheit, 1.8 times that plus 32. But anyway, that's nice to swim in. Imagine swimming in the Arctic Ocean. It's like Santa Claus spa or something. It's pretty nice. There is a tropical rainforest in England. The Arctic was possibly as much as 40 degrees Celsius warmer than it is today. And in fact, if you would go to like Ellesmere Island, which is one of those Arctic islands in Canada today, you would have seen an environment very much what's like outside, we're here in Houston, Texas, where I'm filming this. You would have seen an environment much like what's here, where there's palm trees and alligators and tortoises and all kinds of diverse mammals and this amazing kind of almost subtropical ecosystem at 79 degrees north latitude. That's how warm things were in this Paleocene, Eocene thermal maximum. Now, it wasn't completely wonderful. You might be thinking, hey, tropics in Canada. There was an extinction at this time. Some of those little foraminifera that live in the oceans actually went extinct, and this is because there was an increase in ocean acidity, which affected those organisms. Now, following this event, we have a global cooling event that led to the Ice Age, what we call the Ice Age, meaning the most recent one. Now, this overall cooling event, like I said, was interrupted by a little bump of warming during the Miocene. All right, the Pleistocene and the Holocene. So this is really when we're looking at the Ice Age. In fact, we're still in an Ice Age. An Ice Age is defined as an overall cold period where we have large ice sheets covering parts of the world, which is what we have right now. So we are now entering the Ice Age of the Pleistocene and Holocene, the last 2.58 million years. Something very important happens during this time. Hominids evolve. That's us. So this is when our family, our group of organisms finally shows up on Earth. And we do have this Pleistocene Ice Age, this overall extra cold time period where a third of the land was covered by ice at its absolute maximum. This is what we can see right here. You can see here's the Antarctic ice sheet. This is sea ice. Here's in North America and Greenland, and there's again the sea ice covering that area. And you can see all these places that would have been covered by ice and snow during this time. Now, what this does, this ice cover ends up shifting climate zones southward in the northern hemisphere, and of course northward in the southern hemisphere. And what we mean by that is For instance, your tundra gets shifted southward, so that would be in where the Great Plains are today. Your subtropical area would get shifted southward, and so we have a very interesting, very different climate that we would see at this time. We also have major erosion of mountains, because in the mountains we get ice covering those areas, glaciers covering those areas, and glaciers are very efficient at grinding up the rock underneath them. And so we have major erosion and shaping of mountains at this time. And what's fascinating in ice ages is we get more rain in some areas, but less rain in others. So for instance, the Sahara was drier at this time than it was today. They were getting less rain there. But if we would go to the deserts of North America, they were getting more rain, so they were wetter than what we have today. So this Pleistocene ice age, the Pleistocene begins about 2.58 million years ago, and our most extensive glaciation is about 1 million years ago. And the Pleistocene was originally divided into 4 main glacial interglacial cycles. So an ice age is an overall cold time period, but it does have these warmer time periods in between called interglacials, kind of like what we're living in right now. But even the early people who were studying this studied everything on land, and they saw 4 main glacial interglacial cycles. There's actually a lot more of those. They're better preserved in the oceans, where new ice can't basically plow over and erase the older records. So once we started having this ocean drilling project, where these research vessels sail all over the oceans and drill into the sediments and recover stuff, we originally thought it was 4, but now that we have all this data from the sea floor, we know there's over 30 glacial interglacial cycles. And what you often see in here, this graph is showing some of the glacial interglacial cycles over the past 400,000 years. Here's today, there's 400,000 years ago. In blue, we have the temperature record. Where it's higher, it's hotter. Where it's lower, it's colder. So we can see some of those interglacials. In green is the carbon dioxide concentration. And in red is dust, and of course dust is going to be related how much the rocks have been ground up underneath the glaciers, and then as the glaciers melt, how it gets blown around. Alright, so the results of this ice age. Sea level is going to rise and fall. These are those small scale sea level changes that are related to how much ice there is on the planet. At the maximum extent, sea level was about 120 meters lower than it was today. And Britain and Europe were actually joined. There was no English Channel separating them. There was no Bering Straits separating Asia and North America. So we had the Bering Land Bridge. And this base level, because sea level is ultimate base level, if sea level drops, that means streams can carve downward farther than when sea level is higher. And so this affects canyon cutting, and then estuaries, which are when sea level rises, all of these stream systems get flooded by seawater. So we see quite a bit of the landscape being shaped, not just individually by the glaciers, but also because of how sea level is changing at this time. So this is Europe, and showing the ice on land in Europe, and this is southern Britain, this is France going into Germany. All of this right here, this darker green, is water today, but at this time you would have been able to walk from England into France. This always makes me, as a geoarchaeologist, think about how many archaeological sites are in that area that have been submerged under seawater as the water has risen. Now, in addition to the sea level changing, we're also going to have glacial rebound occurring. These these glaciers were sometimes 3 to 5 kilometers thick. And that's a lot of weight to add to the crust. Because of isostasy, that would push the crust downwards. Well, once those glaciers melt, now we don't have that weight pushing the crust downwards, it's going to start rising again. That's this glacial rebound. And we see that in some areas, like, for example, Scandinavia. Over here in these red colors, that's land uplift of a centimeter per year or more. That means the land is rising this much every year. And that's focused especially where the ice was the thickest. Okay. In North America, the ice from the Ice Age created the Great Lakes. Lake Huron, Ontario, Michigan, Erie, and Superior. But it also created a number of smaller lakes as well. The Great Lakes were created in places, often you'd have softer rocks or old river valleys that were easy for those glaciers to erode and sculpt, and then when the glaciers melted, those low areas were filled in with water. But you also have, for instance, in Michigan and Wisconsin, other glaciated places like Minnesota, it's the land of 10,000 lakes. Those lakes are really ponds, they're kettle lakes. These kettle lakes are shaped by glaciers, by the glacial ice melting as the glacier disappears when temperatures rise. But then we get some of these fascinating lakes, like ice-dammed lakes. So the glaciers, as they would grow, they would sometimes dam off areas and hold water behind them. We had this huge ice-dammed lake called Lake Agassiz that existed. You can see it covered parts of North Dakota, Minnesota, and then Manitoba and Ontario and so on. But in the United States, we had Glacial Lake Missoula. So this part of Montana was all underwater, and there was this ice dam that was holding all that water back. And that was pretty interesting, having this lake there in the middle of Montana. Now we also have what are called pluvial lakes. Now pluvial refers to extra rainfall. And remember I said the western United States in the Ice Age, we get extra rainfall. So where we have deserts today, this is western New Mexico, that's the plains of San Agustin, that was a lake. This is Death Valley. Death Valley today is known for being so dry, but there is a lake called Lake Manly that sat in Death Valley. And here's the Great Salt Lake. The Great Salt Lake is all that's left of Lake Bonneville, which was one of these big pluvial lakes. And those were created in the western U.S. simply because the climate was different, we had more rainfall, we had less evaporation, and so instead of desert, we could have kind of more of an area of grasslands dotted with lakes. So if you go to New Mexico at that time, not really so much desert, but like I said, more prairie-ish at the time. All right, but let's go back to these glacial lakes, those ice dam lakes, because we're going to visit a place known as the channeled scablands. And the channeled scablands cover a large area of Washington State. And they were created, well, let me just go back a little bit. For a long time, they were kind of a mystery. They're this place where we can see that there's these waterfalls that were huge, but they're dried out now. There's not really big streams anymore. There's places where there's these just random giant boulders sitting in places, and there's actually giant ripple marks in places, and there's this question of like, how could all these weird landforms form? And it comes all the way back to Glacial Lake Missoula in this ice dam. So here are some of those giant ripple marks. This is a road just to show you how big those ripple marks are. And what happened to create these channeled scablands is this ice dam eventually broke, and the entire Glacial Lake Missoula just in an instant flowed out over over this landscape. So imagine the worst catastrophic flood ever just racing across the landscape, and it had so much power it could pick up those big boulders, and it could create these ripple marks that aren't centimeters high but are hills in themselves, and basically raced off to the Pacific Ocean. And so these channeled scablands in these places like these giant ripple marks were created in this giant flood created as Glacial Lake Missoula drained. We also, from the Ice Age, get a whole lot of loess deposited. Loess is basically silt and clay. It's very fine-grained sediment. You can imagine under the glaciers, I said they're really, really good at grinding up sediment, grinding up rock. Then as the glaciers retreat, all of this ground up rock is left exposed that wind can then pick up and drop off in places. And that's what loess is. It's this wind-blown silt and clay. We can see in the United States we have quite a bit of this silt and clay that was deposited as wind carried it there from the receding glaciers. All right, so ice ages end up shaping the planet, but we got to figure out, why do we get these ice ages and interglacials?